Good afternoon, viewers. Today we will be studying the numerical analysis in work power energy and friction. First of all, let us revise what we mean by work. In physics, work is said to be done when a body acted upon by a force moves through some distance in the direction of the force. Work is given as the dot product of force and displacement, or work is Fs cos theta. If theta is 0 degrees, work done is F into S, that is maximum work is done when a force acting on the body moves the body in the same direction as that of the force. Then what is the work done in moving a body over a rough plane surface? Force of friction always acts in opposition to the motion of the body. Suppose the body moves through a certain distance S, weight of the body acts in the downward direction, normal reaction acts in the upward direction. So, minimum force required will be equal to force of friction. Force of friction is equal to mu r, r is equal to mg. This means F is equal to mu mg. So, work done is F into S, mu mg into S. Then is acceleration of a body down a rough inclined plane. So, let us suppose that we have an inclined plane, a body is lying on it, angle of inclination is theta, weight of the body always acts in the downward direction, normal reaction acts in the upward direction, that is normal to the body. So, the various forces that act on the body are normal reaction, which acts normal to the body, body the normally, body the perpendicularly. Secondly, weight of the body which always acts in a direction vertically downwards. Now, you resolve this weight into its rectangular components, two mutually perpendicular rectangular components. If this angle is theta, you see this is 90 degrees, this angle is 90 minus theta. So, this angle is 90 minus 90 minus theta, theta. So, this component is mg cos theta and this component is mg sin theta. Third force that acts is force of friction. If the body is accelerating downwards, force of friction is always in opposition to the motion of the body. So, net force downwards is equal to mg sin theta minus the force of friction. Force of friction is equal to mu r. R is being balanced by mg cos theta, mu mg cos theta. So, the force that acts vertically downwards is mg sin theta minus mu mg cos theta, and then acceleration will be g sin theta minus mu cos theta, because force is mass into acceleration. Mass cancels out, we are left with g sin theta minus mu cos theta. Now, if the body is to be moved upwards, the body is to be moved up the inclined plane, angle of inclination is theta. As I told you, weight acts vertically downwards, normal reaction normal to the body, components of weight mg cos theta, mg sin theta. So, body is to be moved upwards here, say the body is to be moved by a distance s, what force should I apply? Now, as the body is moving upwards, force of friction will also be in the downward direction. So, the net force that we will have to apply is mg sin theta plus F. But force of friction is equal to mu r. R is balancing mg cos theta. We get mu mg cos theta. So, the force required to move the body upwards is mg sin theta plus mu mg cos theta mg sin theta plus mu cos theta. Now, the work done to move the body through a distance s is given by F into S. So, work done will be mg s sin theta plus mu cos theta. Power, a rate of doing work, work done per unit time. Work is force into displacement. Displacement over time is velocity. So, force into velocity. Kinetic energy, half mv square potential energy mgh work energy theorem gives that work done by a force on a body will be equal to the change in kinetic energy of the body half mv square minus half mu square, where v is the final velocity and u is the initial velocity. So, these are the formulae that we will come across while doing the numericals on work power energy. Let us take up the first numerical. Find the work done in lifting a mass of 4 kg through a height of 2 meters. Mass of the body is m, weight of the body is mg. The height to which this body is to be taken is h. So, the minimum force that you will require is equal to the weight of the body, that is m into g. M is 4, g is 9.8. Formula for work done is F into S. S here is height. So, work done is mgh or 4 into 9.8 into 2. Gives you 78.4 joules. Next question. A body requires a force of 25 Newton to move it through a horizontal distance of 30 meters. Calculate work done if the force makes an angle of 30 degrees with the horizontal. So, here we are given the force, we are given the distance through which the body is to move, we have to find out the work done by the force, but the force is making an angle of 30 degrees with the horizontal. The body moves through a distance of 30 meters. So, distance moved is 30 meters, force is given to be 25 Newton, angle is 30 degrees, work done is given by F dot S, that is F s cos theta 25 into 30 into cos of 30 degrees, (750) cos 30 is under root 3 by 2, 375 under root 3 joule is the work done. Value of under root 3 you should remember 1.732, and if you calculate this will come out to be 649.5 joules. Next question, how much work will be done in dragging a body of mass 100 kg through a distance of 50 meter on a level road if coefficient of friction is 0.25. Now, in this question we have to find out the work done to drag a body on a road which has friction. Mass of the body is 100 kg. So, first of all you should write down what is given to you. Distance through which the body is to be moved is given as 50 meter. G you know is 9.8 meter per second square. Coefficient of friction mu is given to you as 0.25. So, these are the things that are given to us. Now, work done, we derive this relation is equal to mu m g into s. Mu is 0.25, m is 100, g is 9.8 and the distance through which it is to be moved is 50 meters. So, 0.25 into 980 into 50, and if you calculate this will come out to be 12250 12,250 joules. So, these are the simple numericals on work, power, energy. Now, let us take up a bit difficult one. An engine of 100 kilowatt draws a train of total mass 10 into 10 the power 4 kg up an inclination of 1 in 50. The frictional resistance is 4 kg weight per 1000 kg. He says calculate maximum speed. So, first of all, let us see what are the things given to us. We are given power of the engine 100 kilowatt, 100 into 10 the power 3 watt, 10 the power 5 watt. Then you are given mass 10 into 10 to the power 4 kg, frictional resistance 4 kg weight per 1000 kg. So, frictional resistance 1000 kg पीछे 4 किलोग्राम वेट, अगर 10 to the power 5 kg होवे तो you get 400 kg weight. 1 kg weight is 9.8 Newton. You can approximate it to 10 Newton here. So, 400 into 10, 4000 Newton. This is the force of friction that is acting on the body. Now, the body is moving up an inclined plane. When it is given 1 in 50 means you are given sin theta equal to 1 by 50. We have to find out velocity. We will use the formula power equal to force into velocity. So, we need to know the force, how much force is acting on the body. This is mg sin theta plus the frictional force. So, force that acts is mg sin theta plus frictional force. Frictional force ਅਸੀਂ calculate ਕੀਤਾ ਸੀ 4000 Newton. Mass is given to us as 10 to the power 5 kgs. G we are taking as 10 meter per second square. Sin theta is 1 by 50. So, you get 0 cancel there, 10 to the power 4 into 10 by 5 plus 4000. Or you get 5 to the 10, 20,000 plus 4,000. 24,000. So many newtons. Power 10 to the power 5 divided by 24,000. So, this will give us the velocity. Next question. A car of mass 500 kg is moving at a speed of 36 kilometer per hour. If the car is brought to rest in 5 meter, calculate the average force required to stop it. So, there is a car whose mass is 500 kg moving with a speed of 36 kilometer per hour. Car is brought to rest in 5 meters. So, you are given mass of the car to be 500 kg. Speed of the car 36 kilometer per hour. 36 into 1000 divided by 60 into 60, or you can directly write down 36 into 5 by 18 meter per second, because if you calculate 1000 divided by 3600, this will give you 5 by 18, 18 twos are 36, 10 meter per second is the speed of the car. Now, the car is stopped by a certain force. So, work done by the force in stopping the car should be equal to change in kinetic energy of the car. Work energy theorem ਦੇ ਵਿੱਚ ਅਸੀਂ ਪੜ੍ਹਿਆ ਸੀ, work done by the force on a body is equal to the change in kinetic energy of the car. Finally, the car has stopped. This means its final kinetic energy is 0. So, initial kinetic energy is half mv square. Work done F into S. S is also given to us, how much? 5 meters. So, F into 5 is equal to half into 500 into V square 10 square. You get F equal to half into 500, 10 square means 100, 250 gives you 100, 50 into 500 will give you the answer.